All right, welcome back, everybody, to the Additive Snack Podcast. I'm your host, Fabian Alefeld, and I'm super excited today to have Alex Oster here with us. Alex is the Director of Additive Manufacturing at Autodesk, and therefore, as you can imagine, is a very influential person in the industry. He has a very long history and background in additive manufacturing, which of course we will talk about. So get really excited to learn a bit more about Alex, get excited to learn about Autodesk, even his history with Netfabb, but mainly we'll also spend some time talking about the market dynamics, and some of the interesting innovation that is happening in that space. So therefore, without any further ado, Alex, welcome to Additive Snack. It's awesome to have you.
Great. Thank you first for inviting me. I've been a long-time fan and I'm very happy to be here. So thank you.
Awesome. You have a really extensive experience in additive manufacturing. And I'm also kind of curious how you got into the technology. I think you've been around for a long time. So how does a guy from Bavaria, which I'm actually as well, become the globally responsible person for additive at Autodesk?
Oh, that's a long story. So I started in industry in 1998. That's a long time ago as a student.
Yeah.
So the history goes back. It's actually interesting because you're kind of an EOS podcast, even if you claim you're not. But the interest is very intertwined of Netfabb with EOS in the sense that we were founded a spin-off of a service bureau in Germany, which is probably the largest, maybe the second largest, called FIT.
Mm-hmm.
And that was founded in 1995 by a very well-known founder named Karl Frutte. He's very well-known in Germany and in Europe. And he was one of the first employees of EOS from 1990. I don't know when exactly, 1993, 4 on. And he was also the first application engineer at EOS. And then after a few years, he basically quit and bought a machine and started his own venture to.
Yeah, there's a few guys that have done that at EOS, right?
Yeah, so EOS. So I mean, the whole Hans Lange empire is basically has been created around from very active entrepreneurial, spiritual people, and Karl Frutte was one of them, and he founded FIT in his hometown, which is in the north of Bavaria, or in the center of Bavaria. And I just happened to play in the same ping pong club as him. And he needed experienced software people, but he was a very small company and couldn't afford a real software developer. So I started as a student and worked with him from 1998 on to do all kinds of software. We started with an ERP system and an automatic quoting system. And over the years, we amassed a lot of software in-house that just ran the manufacturing organization. And we also grew the service business from 10 people in the beginning to on the height, maybe 300.
Wow.
With a huge enterprise. And I come to that because there were many stages, and EOS was always a steady companion in that, because a lot of the machines, I mean, we had every machine, a lot of different machine technologies, but of course EOS from the history was always very close, especially in plastics, but also in metal. So we had, I think you were one of the first who did from 2000 on, I think. We did injection molding with additive manufactured tools with SLM machine when they were literally selective laser sintering machines. So it was called DMLS at the time because the laser power was not enough.
You still had bronze
melted power.
Yeah,
but it was like a copper alloy something, and you basically had to. It was not as strong and so on, but we could make fast injection molding inserts with it.
Okay.
And I think we probably were not the first in Germany who did this, but we were definitely the first who did that profitably and not in a university research organization context. And that was very early. I don't want to tell stories from that, but ages ago and not true anymore. But that's how we grew a lot of our custom and what it makes, what it needs to make parts on a profitable basis, and not on a profitable basis, but with a commercial background.
Okay.
And I think that is what a lot of the industry, especially in the heydays of the let's say 2020s or 2015, 2020, when there was the big hype I mean, basically, there came so much capital and fresh knowledge into the industry, and everybody who could spell metal additive manufacturing on a pitch, they could easily get like $100 million from somewhere.
Mm-hmm.
And that was a very exciting time on the other end. I will talk about that because I was at Autodesk at the time already, so I had a lot of insights on what's going on. But it's very different if you have to earn money with the thing you do. And if you're a small Southern German company that is in a manufacturing space and have a lot of automotive customers, the way you operate is very different as if you sit on nothing against the venture model, but if you sit on $100 million, you just set up your business different. Yeah. And I think what we're seeing recently is that in manufacturing, if you don't have this exponential scaling, because you always have like a linear component to it, it's very hard to justify the wastefulness of a massive budget that you just introduce in an organization. But if you just don't have money, you find other ways to make things happen. And that's basically where we come from. Yeah, and that's why we also developed a lot of software in-house, because we just couldn't afford like other software. And we just tried to make software for our customers to deliver. And it was an amazing time in a way.
And I'm guessing there was also not enough additive specific software out there that met your needs. Is that also a reason?
I mean, there was additive software, but of course, it's the one thing there was definitely not enough flexibility in the market at the time that allows you to do kind of like custom tool passing, kind of things. I mean, that was very foreign. I mean, people, how should I say that on a EOS software? I mean, at that time, you were really lucky if you could change the laser power on the machine. And I think the industrial mindset of the machine vendors has shifted a lot. Yeah. But this was very much at the beginning. And we developed so much software that we, of course, even if you don't have much money, you need to hire more people if you do broader things. Like we basically made all of our nesting in-house and all of our ERP system and all of our machine control and all kind of things. And at some point you have too many people. And then in 2008, our founder said that we need to earn our own money because it's just getting too expensive to hire like half a dozen people just to develop in-house software. And that's when we created NetFab as a software company and tried to sell it.
Okay, so spun it out of the FIT.
Okay. And that was an interesting time. I think the first customer was EOS and the second customer was Stratasys and the third customer BMW. So, I mean, this was like this. It was a very small industry. Everybody knew everybody, and we had a few special tools for like analysis of slice distribution and all this kind of thing. So that's what we sold in the beginning. And then in 2000, what we then commercialized was a tool for lattice structures creation that we developed from 2004, 2005 on. That was a very novel approach. And we were basically pushed to it because we did injection molding tools. And then we had the struggle with the material of the laser systems, like the EOS systems. And then Arcam came along, the Swedish company that was then later acquired by GE, and they sold electron beam melting systems, which was fantastic because they sold us that you can do real metals and sold it on the premise that you can do injection molding tools with it. And because Culfruit always buys the first machine of anything to just see where the market is going, we just bought the first machine. I think it was not the first on the world because there was a secret one before, but it was the first officially known that they sold.
Interesting.
And we had it. And like every first machine you buy, it didn't work very well. And what we figured out after a few weeks was very quickly that you can make anything with this, but not injection molding tools from like an accuracy standpoint. But if you could like buy parts, it would like, they would like break in the middle and stuff.
Okay.
And then I call it the problem, or we had the problem that we just spent $500,000 on this machine, or how much we paid, and we needed to find another space.
Mm-hmm.
And the big advantage of that machine was because it used an electron beam, is it could, in a vacuum, it could print pure titanium, which the laser systems at the time were like years away from being able to. So we went into medical, and in medical, you quickly come to, could we make a lattice structure? Because that's something new, and that's something you can not make in any other way.
Yeah.
And that's how we got into lattice design. And then there was really no software at the time to make a complex lattice structure. So we really had to write it on our own.
Okay.
And that was like 2006, 2007. And then we commercialized it 2009 or something. And we quickly found out then in 2009, we had this very specialized software that did lattice structures and slicing and all those kind of things. And it's, I think it still had features that nobody else in the market has, which is funny. So if anybody listens and wants to know about it, I'm happy to say it. But of course, what quickly happened was we sold the software pretty expensive because it was a very, very niche. I mean, nobody had a machine at that time that could actually make use of it.
Okay.
So I think we sold it for 30,000 euros or something. And the first it did, if you gave it like a broken SDL file, so the first that happened was it crashed. And that creates, I mean, if you build a company, that's what happened. And then what you do is, I mean, you need to mitigate it, make your customers happy. So we added repair functionality and generic data prep functionality to the software. And that was interesting because I don't know how we ever got to this, but we basically gave away everything except the latticing away for free because we didn't have a marketing. We didn't have, I mean, we were like Southern Bavarians. We didn't have a US presence, and it was very difficult to really get market traction. So we just gave away a free version that could repair SDL files. Because at that time, there was commercial software, but it started at like $10,000 per year.
Okay.
And there were like 2-3 different brands that could like fix your SDL problems. And that was $10,000 per year. And it was fine for a specialist machine prototyping market that additive manufacturing was at the time. So they had all viewers, but you didn't have the capability. If you wanted to change one triangle, it was like, it cost like a fortune, which was not a problem in the industry. I mean, I don't want to dismiss anything. This was how the world was. But what then was our big luck is what happened was that the FDM revolution happened. And that informed a lot of my thinking about what the industry will do because and we were the first ones at Euromold, it was at that time still. We were the first ones who got to know it because we had a free software. And all these people who were in the RepRap community who had like crappy SDL files from the CAD systems, they needed a software and they could not have the means to get like a $10,000 SDL repair software. And there was no free alternative. So they all used NetShop within like a month. And so we were basically the first to introduce the FDM hobbyist world into Euromold. I think we were the first to had like FDM printers on the booth in 2010. It was like $800, which was like a step change from the 250,000 before. And that was a really fun time. I mean, the quality of these machines was like really crappy. And we had a lot of hybrids at the time. I think we also made our own machine, which then got us in trouble with the new machine vendors and all those kind of things. But this was basically where we came from. And we really tried to do the data preparation for really now well-known or used to be well-known brands like Ultimaker, for example, shipped for a few years NetShop with the machines and so on until they were big enough to do Cura. And that was a really interesting time for us. And not only that, it was, or we collaborated with Formlabs in the beginning, for example. So because they were then the second wave. So the first wave was the FDM wave, and then there came the SLA wave. Where Formlabs really, and Max is really killing it with leading the best business in industry, I think. Because there is a lot of competition from Asia, and he is just like competing against it. And I think it's very underrated how great of a company leader Max Lebowski is at it.
Yeah.
The Formlabs CEO. And sorry if I talk too long, just stop.
No, you're good. You're good. This is super interesting.
And that was an interesting time. And also on the industrial side, I mean, in literally the money we made on the industrial side, this was maybe just like a hobby project where we had a few people working, and it was really good because it was relatable. And we feel that now in industry. So every engineering student, and we come to workforce development like maybe end of the hour. It was very different. Nobody you've met, no engineer you met on the street had a clue about additive manufacturing. It was a little bit, maybe somebody knew that you do prototyping with it, with SLA or whatever.
Yeah.
But you didn't, it was very exotic. And with this FDM, so there are two things then, this mass marketization I call it commoditization of of the FDM space helped the industry. One was that the knowledge about 3D printing and the thought processes. If somebody who has printed a lot of FDM parts in their lives, and I think you see that in industry space probably, has a lot easier times to make successful products with additive.
100%. Yeah.
And nowadays, every engineering student has a 3D printer because, I mean, you can just buy a Prusa for a few $100, and it's just, you wouldn't be an engineering student if you wouldn't do that.
Yeah, there is no university anymore that doesn't have FDM printers accessible for students. Totally.
And the second thing is, and that is actually the more funny thing for us, was really great, and that created a lot of growth potential for us, was the American way of marketing things.
Okay.
To say it cautiously. Because there was this guy called Brie Pettis, and I mean, Brie is amazing. I mean, he got some beating because he was more an outgoing manager than like execution focused, if you understand. That's then the flip side of the American model. But he really popularized the way how additives manufacture 3D printing was known. So he stood in front on top, and then the cover of the Time magazine with this little cupcake maker bot, which was made out of wood, and basically literally told the story that this machine will ship back our jobs from China, which is a really good story. And that had a lot of consequences. For example, a lot of C-level executives that flew around in the world, they just, on their first class, business class seats, they got the Time magazine, and then they read the story of Brie Pettis and this machine that will ship back our jobs from China. And the next thing they did is they asked the R&D department, what do we do in additive manufacturing? And of course, the answer was nothing.
Yeah.
And then if the CEO asked that, then there's panic, and there's an incubation business started, or incubation group that explores options. And what do? They call at places that do that for many years. And that was like our headquarters in Passberg in Germany, because we were one of the few who really had actually produced feasible products with additive manufacturing. So we got a lot of traction on the industrial side just because the popularity that the FDM space created.
That's interesting. Okay.
But that was a long time ago. And then this was like 2011 and on the industrial side. And we really grew the business a lot. So I think in 2012 or so, I think FIT bought, that was the year where the SLM 500 started, which I think is a very much underrated machine in the industry's history. Because it was 4 laser first time, big build envelope, open system, like you can do custom tool passes.
Yeah.
And then like our founder really bought just like 10 at the time. But at a time where nobody, like it was big news if one machine was sold, and he just bought like 10 SLM 500s.
Wow.
And that was a big thing because we suddenly had the largest metal capacity in the world for many years. And we had an open system, so we could run our own tool passes on it and our own developments. And we printed a lot of aluminum, for example. And we really could go after casting applications. And that was a great story. And that just catapulted us into serious manufacturing at a time where nobody was near it, I think. And nobody, people will find offensive. But like,
sure,
it was not so common at that time. That was 2012, 2013. And then,
I mean, even today,
having
having 10 metal machines is a pretty big operation still, right?
Yeah, and I mean, FIT has many more.
For
So
that time,
maybe about 50, 60, a lot of, you also have M400. They also, I mean, I'm out now, but they have also a lot of M400s and so on. But like the SLM 500 was, I think, an industrialization step that you wouldn't underestimate, because I mean, we had like SLM 280s and we had like M280s and what was common at the time, which was great for tooling and other applications. But then if you could make larger parts with more slashes and so on, that was a big thing, and multi-laser. And also, I mean, that is, has also a thing. I mean, printing then custom tool parts on the machine and optimize. And it's not so much that the material parameters are that was always the tension. It is still the tension that who develops the process parameters. But in my opinion, the tier one suppliers and the people who actually operate the machine, they really need to tune the process parameters, because
I agree.
You need to tune the process. I mean, your additive, like the additive minds business. I mean, that is what EOS and everybody has understood now. But at the time, it wasn't at all. And it's really, you can't make a commercially viable business if you don't tune your exposure strategy to the actual geometry you want to build. And we made a great video with SLM at the time. Is actually did not take off because it was too German and too attention to detail. You need to watch 10 minutes to get the gist. So it was like, from that sense, it was not that great American style, but it was a really good video that explains all these kind of things and all the development loops you need to put into making application work. And that goes back to the CAD and to the design of the system, because also like the story, it's less popular now. It's still popular, I think. Maybe in your sales team, it's still popular. But then you go out and say, oh, with additive, you don't need to do design for manufacturing anymore. I mean, that was the notion like 10 years ago, because you can do anything, you can make anything.
Yeah, the freedom of design.
Freedom of design. And that is just not true. It might be better than in other technologies, but it's not like fundamentally different. It's just like you follow different rules that for milling and for car. And yeah, that's where it was. And then in 2015, and then we quickly went into real industrial application and use cases, and suddenly the CAD companies were interested in this space.
Okay.
And especially Autodesk. So Autodesk bought a lot of companies before us. They were like on an acquisition spree in the additive space. And in parallel, they invested a lot in additive. They bought, for example, Within, which was very connected to EOS at the time. It was also basically our competition in terms of latticing, because they did just beam lattices that were like more rule based, and they had like FEA integration and more organic. So they made really fancy parts with EOS at the time. So Autodesk acquired Within, and then Autodesk acquired Netfabb in 2015, which was also. So what happened in parallel is that Microsoft was interested in 3D printing because of the FDM hype. And they invested so much. I don't know if you remember, but they invested so much into additive manufacturing.
I don't remember that at all.
So I think I always joke that it's all Bill Gates' fault, because he was at the time, he was chief innovation officer at Microsoft. And he did like this 10-point plan, which technologies will be important in the future. And 3D printing was one of them because of pre-Pettis. And that must have been 2013, 14. And he basically meant, and then what big companies do. So they took from the chief innovation officer, they took this mandate and made like an incubation board, and like VR, I think, was another one. So that's where the HoloLens came. And so they created a big units that dealt with the different verticals, and 3D printing was one of them. So they had a great development. I mean, I got to know them in person. I mean, they were great people, and they just added 3D printing to Windows because that was their mandate. And so today you have 3D viewers in Windows. Yeah. At the time, you could buy MakerBots in the Microsoft stores and attach them to your USB drive, and it would say 3D printer found. And then you could literally print from your CAD system over the print dialog in Windows. That's still all in Windows 10. So with Windows 10, they created this. And they I don't know how much energy they put into it. They created an app like 3D Builder. And they worked a lot with us, because they worked with all these FDM printer manufacturer companies that came up, and there were like three hardware people that just went after the hype.
Yeah.
And nobody had software expertise. So they basically said, yeah, we don't have much software expertise, but for data preparation we use this little free tool called NetFab here. And then they did their research, and then somebody from Redmond called us and invited us to Redmond to do something together. And then we did a co-branded NetFab service where people could repair their SDI files. And yeah, I'm talking too much about the history.
No, I love it.
And that was a great thing, because we also created this 3MF consortium with that, because Microsoft was a seriously, how should I say, neutral player in this space. So Microsoft was not a threat to the machine vendors, and it was not a threat to the CAD vendors in a way. So they could like basically define a format, and they did it out of necessity, because they for this all integration into Windows, they needed a pipeline format like what XPS, I don't know if you know XPS, what PDF is, basically like something richer than SDL. And that's how they defined their own thing. And because because they lost the big XPS versus PDF war in the very ages ago. They completely changed their model and basically just open sourced it and created a consortium of industry leaders to maintain and guard it. That it's not the Microsoft thing. And so we got Hewlett Packard joining, which is really great because they were really pushing it. And we got like SolidWorks joining in the beginning, and then Autodesk was very quickly with all its investment also joining, because what the hell is doing HP with SolidWorks?
Yeah.
And then Siemens was very interested. All these like players in the CAD space came, and then also all the machine vendors, like EOS, for example, was very interested what all these CAD players do with Hewlett Packard. So we by one we got like also the major machine vendors joining, and it was a great technical consortium to advance the file format and the ecosystem in 3D printing. And I have to thank EOS how much energy they have contributed over the last years. I don't know if you even know, but they have like an implicit spec now and all this kind of thing. So I think it's really important on a technical basis that we have the solid craftsmanship in the industry to advance industrial applications. And we are so short from being ISO certified in the 3MEF consortium. I think it's already approved. It will be published within the next week, so that will be very interesting too. So we go that path. And yes, so everybody who has a software interoperability issue with 3MEF, it will be so much easier. But that is a different story. Why I told this is because if you are the only small company in a group of many people from big industries, then you quickly get into more serious talks. And that's how we ended up at Autodesk. So we got in contact with Autodesk and had very interesting meetings, and then they acquired us within a few weeks. So that was for a small Bavarian company to be acquired by a
global player,
by a global CAD player that's based in San Francisco. That was a really interesting journey. And yeah, this is nothing for a public talk, but I can tell a lot about stories, what you experience with it. And that's our journey since then. So since 2015, NetFab is an official Autodesk product, and it still exists. And we have an amazing customer base. I can't stress that too much. I mean, we have thousands of customers. I know, for example, I know that we have like millions of medical parts that have been printed with NetFab, and or let's say millions of dental parts and 100,000 of medical parts. We have I know at least a dozen parts that have flown to space that were done with NetFab. So we have a really nice end-to-end software portfolio that does everything from data preparation, CAD integration. We used a lot of Autodesk technology that we put into Autodesk NetFab, like the Inventor CAD kernel, for example, and all the slicing technology and all the mesh technology that Autodesk had to offer. So we also made Mesh Mixer at some point. That is a very popular tool in the 3D printing industry. And that creates a great ecosystem. And I think NetFab has grown into an established software package that many people rely on. And it was not clear 15 years ago that we would end up in that space. And that's very humbling in a way if you look back retrospective. But that is, of course, not very dense because, Autodesk acquired, big companies acquire not for playing the small game that a data prep niche tool would do. And I'm actually very thankful how they treated us in a way. So they basically consolidated all the additive developments under one umbrella. And then what Autodesk does is it's acquired many manufacturing verticals. And I don't know if anybody knows what Autodesk is. Autodesk is one of the big CAD companies, and of course we do CAD, but they also acquired Delcam, for example, which was probably the leading CAM company in milling and turning and Swiss machining and all kinds of machining tools.
Okay.
That was one of the big players, and they integrated it. And then they acquired Moldflow, for example, which is injection molding simulation company.
Okay.
The leading one.
Interesting.
They acquired a company that did composite manufacturing, acquired a company that did sheet metal nesting. So in every vertical, and together with Autodesk acquired.
So they acquired all these specialized tools in all these verticals.
Very specialized tools. And then the strategy in hindsight, the strategy, I don't know if it was always that straightforward, was always that one of their own, these tools exist and still exist. And that is great because we're the only CAD company who has a specialist tool in every vertical, but then made the effort to create an integrated tool, which is Autodesk Fusion.
Oh, okay.
And by accident, it's called Fusion. So it's the fusion of all these things that Autodesk acquired from the CAD, which came from Inventor, which is a really robust state-of-the-art CAD system, plus all the CAM systems and the like subtractive and additive and nesting and composites.
Okay, so initially it was called Fusion 360, and I guess that 360 means 360 degrees across all manufacturing verticals. Is that correct?
Yeah,
okay.
Yeah. I mean,
okay.
And
now you dropped.
That's a little bit the American how you phrase it, but the 360 is nice because I always paint Fusion as a little bit like an Office 365 of design and manufacturing.
Mm-hmm.
So it basically gives you a universal toolbox that anybody that gives you a lot of functionality, but that doesn't help. It gives you a lot of functionality on the same data model in a parametric way, which means if you change something in one place, like for example, you change the hole diameter on your CAD model,
mm-hmm.
it automatically updates all the support structures that are attached to your hole and also all the milling operations, like the drilling operations or whatever that come after for the post-processing.
Okay.
And that's a very unique thing that you only can do is if you put a lot of energy into like the end-to-end architecture and backend. But then also you add a lot of vertical functionality, which is really important that they acquired. And then you need to, and that even that doesn't help you because you also need to make it easy to use and affordable.
Mm-hmm.
Because otherwise you have a specialist tool that has like 50 million buttons.
Yeah.
And that is really hard to scale, not only as a business, but also as a like
from
advancing the industry. And we see that clearly. I mean, we see that in the additive space. We see that also in the injection molding space, for example. There are not so many plastics engineers out there. So what our simulation team did, our mold flow team, is they took mold flow, which is really like top line, scientifically proven. I mean, it changed the injection molding industry like 30 years ago because people went from guesswork to simulated data.
Mm-hmm.
that then could drive their tooling decision. But it's really hard. I mean, I shouldn't say it. You need to be a specialist to use it. And then this reframing from specialist tool that is for very few people to something that the generalist engineer can use.
Yeah.
Maybe not to like 100% as sophisticated that specialist who does it every day uses, but like to a way that you can get something out. And that is great. I mean, I have no idea about CAD. I'm a software engineer. Actually, I'm not even a software engineer. I'm a mathematician from southern Bavaria, so I have no idea about CAD, but even I can use Fusion because they put a lot of energy, or we put a lot of energy in making it accessible and easy to use and like intuitive in a way that allows you to get into it and work with something. And together with a relatively mass market compatible price point, that has been a really great success story. And you see that also in the additive space. So if you go to Fornex, for example, in the hall, everybody loves Fusion. And a lot of the example parts that you see in the halls that were designed in Fusion, because of course you can use a super specialized high-end CAD system for some things, but you don't need to. And Fusion has like free surface modeling, organic modeling. It's really amazing for additive manufacturing. And then we added all the NetFab functionality into it. I mean, I didn't even get to that. So we have like, we support, I think about 300 machines now, from FDM to SLS to SLA, and of course, laser SLM machines, like probably every SLM machine in the market, including process simulation, which is our mold flow equivalent. So for plastics, it was mold flow. For I should shout that out too. For metal additive, for DD and SLM, Autodesk acquired the first predictive solver technology out of Penn State called Penn Computing in 2015 or so.
Oh, okay.
And that we also integrated into Fusion. So basically, any Fusion user we have 2 tiers. So we have the base tier, which is like $680 per year, I think. And then we have an extension, which is another $1,500. So for $2,000, you get a metal additive solution that allows you to do support structures, custom tool passing, process simulation, predictive process simulation, and then distortion compensation and all these kind of things.
Wow.
Plus 3 to 5 axis post-processing in the same software environment parametrically. And
Powerful.
we sell it for like $2,000, around $2,000. And I think that's a really game-changing it's a really game-changing offering, in my opinion, that allows you also to extend the reach of additive manufacturing.
Yeah, it lowers the barrier. It lowers the barrier of entry.
It lowers the barrier of entry because even it also if, I mean, I don't want to sell it as the cheap solution. It's a different business model. It's a commoditization way of doing things to make it easy to use and accessible, that you don't have like 1 or 2 seats of a very expensive software package, which we have, which is NetFab simulation. So we have the specialist side of things too, so I don't want to neglect it. But being the only company who has these 2 software pieces in the same group and selling both of them, I mean, I really buy into the fusion story because it really disrupts the market in a way. No, it doesn't disrupt the market. It disrupts the organizations in a way that they can work differently if they have a base platform that can do all of these things. And it can also do FEA and all that. So it's not only for design, and it's also not even forced to design. So you don't need to make your design in Fusion. You, for example, can import your design from a different CAD system. And then you do all your downstream processing. So you can, what people often do is they do defeaturing on the CAD model.
Okay.
And then or change the hole diameters, add like that, the things you do. And then you put it into the manufacturer workspace, and then you create the support structures and
the post-processing.
And do 5-axis post-processing after. So all these kind of things in one software package that is affordable and people can use on a mass scale. I think that is really important on the workforce development. Hey, do we talk about?
Yeah.
That's really important because otherwise it's not affordable. You can't give everybody $50,000 software that wants to play with people.
Well, let's talk about workforce development for a second, because I think there's 2 aspects of it. One is what I would call the professional education space, meaning how do you get existing engineers at companies into the additive space with the lowest barriers possible. And then there's the new workforce development, meaning how do we get high school students into manufacturing, and how do we get college students or even trade school people into the additive manufacturing space, right? So maybe start with the professional education, because that kind of is where we just ended. What type of...
Yeah, we can do education quickly before we forget, because that is very quickly to say.
Okay.
And that is also what I found when I came into Autodesk, is there is this religion here that student software needs to be free. So every Autodesk product, and there are hundreds of them, maybe not every, but like almost every product is like free to students.
Okay.
And we see that very important. I mean, there is, of course, like a own interest in it, but this is really religiously pursued in Autodesk, that the student community is the future and they need to have all the technology accessible to them at the fingertip, because they will develop the next generation. It's also something very much Silicon Valley American. Everybody looks for the 20-year-old. And I think that is on the education side. I think on the professional side, it's much harder because people are usually living in organizations. And it's not only like a technical problem to get them excited or like to develop the skills to change something, but it's also like an organizational barrier, like changing the mindset of an organization. And that is, my opinion, the much harder and long-term issue in additive manufacturing.
Yeah, it's a cultural
There's a lot
change
of trust
for a lot of companies.
It's not only a cultural change. It's also like risk averseness. There is economics. I mean, the parts need to be cheap enough, but need to be economically producible enough. And I think there is a lot of things to do. We can talk about that later. What hinders additive manufacturing adoption. But I think from a software side, what really helps is if you have software that everybody can use, and not only the super specialist. And because that allows generic departments who work on something completely different play with the technology and get like a cost estimation or get like a feasibility study and get like a quick simulation if this part would be printable, if you would print it. Even if you are far too early to invest into machines that would actually make your design and make your parts, you can get the first feel for the technology. And people have this because they use this for FDM all the time.
Sure.
So if somebody who has FDM additive experience, you give the tools to do metal additive manufacturing. I think it's not impossible that they come up with solutions that you can't do in a centralized way. You need to do it in a grassroots level. And I think that is where Fusion Story is great. And we do that a lot with EOS because we recently made a video 1.5 years ago with your head of software, Martin Steuer, which I wanted to shout out. I mean, he's a big believer into
Martin
Fusion,
is
a power user too. And we did a really nice EOS integration. So we have an app store. So we have an EOS app that connects to your machines with your EOS print SDK. And this is very nicely made. I just can advertise that to use. And this was on the metal side, but we also have really good soft on the plastic side. We also have a lot of functionality for people like our 3D nesting. Multi-tray 3D nesting is what we released like a few months ago. They basically just take about 500 of these parts and it tells you like, it nests them into different trays. And that allows you to plan the feasibility, the operations on the plastic side too. So,
okay. So maybe let's double click on one thing that you said, which is transitioning from an FDM, maybe even a hobbyist environment into a metal additive application space. How should companies or engineers approach that from your experience? Is it get Autodesk Fusion and play with it, or is it what's the transition look like from your experience?
That's a difficult. I have a lot of opinions, and I can't come to crying anymore if I said it. But the machine vendors have the wrong incentive models in this.
Okay.
And they did that for 10 years. And that is always a big issue. That is a big issue. For us as service bureau at the time, that was a big issue. But of course, the incentive models of the machine vendor is to sell a machine. So if an OEM wants to make parts, they get the salespeople, and then they get all the salespeople from all the machine vendors, and then they make the pitches for a production environment for a machine. And then the machine vendor sells 2 machines because one is we want to do 2 materials, and everybody's happy. The sales guy's happy, made a sale, everything is awesome. And then the OEM who bought the machine just has a capex investment of like $1.2 million for the machines, and then it needs to fulfill safety requirements, so another $2 million for a powder safe place where you can have powders that don't burn, and then you need to have a team of 10 people that work on it for a few years. And then they make amazing parts. Usually they make beautiful parts they do like application development and make beautiful parts and all these kind of things. Nobody cares about the costs because it's already paid for in big company. And everything is great. One or the other part lands in front of the CEO's desk as like, see how innovative we are. We make additive parts. It's the future. This was like 2020 mode or pre-2009 mode.
Yeah, that was the 2016 to 2019 phase.
Yeah, exactly. And then the problem is after 3 to 5 years, at some point the bean counter comes along and says, how many parts did we produce and how much money did we spend on it? And then the part economics are really bad.
Yeah.
And that kills the technology for many companies. It burns it for like until all the senior management has moved on and somebody else comes in because they know we burned so much money on this technology, didn't work. Cost was 10 times too high because we had all these overhead costs and all these kind of things.
Yeah, that was the issue of the additive hype that you also talked about.
Yeah, but it's still the issue a little bit. So I think the real grassroots. No, I have a lot of opinion. The real grassroots is building parts externally is never wrong. If you have $1 million to make an additive application, invested in the people and in the engineering of these processes to find applications and not invest in the machines directly.
Sure.
And then let third parties deliver the machines that know how to run them. I mean, if you want the casting parts, you don't build your own foundry in the garden to make cast parts.
Yeah.
And maybe they change
there
this one
are-
day with these small machines that come out.
There are great
But
contract manufacturers out there today, right? That
Exactly.
can-
And if you make a PCB, if you want to make, if you make a the custom computer PCB, you don't solder it on your own pick and place machine.
Yeah.
Maybe something. I don't. I'm getting a little bit, but it's kind of interesting that I think that this application development is really important. This was always the problem, that if you burn too much money, you burn for some time, and I think that is one of the reasons why this hype fed off, because it's at some point you have like disappointed every company who can afford to get into additive for a few years, and that what happened, I think, 2020, 2021.
Mm-hmm.
And I think that's where it faded off. And I think these new developments that come that are much more realistic, and there's a lot of depression in industry, which I don't think, because there are literally, we wouldn't fly to space often with these new space companies. And I mean, EOS is big in this game. We wouldn't fly to space with these new space companies, wouldn't be there additive manufacturing, because you really can iterate quickly. You can make these high-end parts. You will make these high-end parts. And that is something that is valuable and valid, and I think the industry will grow and there's a great future. It will be just not special anymore, if you understand what I mean. It will not be the thing, it will not be the disruptive thing that replaces anything. It will be a thing with its place.
Yeah, it's one tool in the manufacturer's tool belts. 100%.
Exactly. And it makes sense for a lot of things, and it makes sense for us things. And I always joke around, I recently gave a talk and I joked around that we usually have two problems with a part if you want to manufacture a part. Either it's too expensive or the quality is not good enough. And if you have both problems, you can forget it.
Mm-hmm.
Then it's really difficult.
Yeah.
And if you only have one problem, I think there's a way around. And I think what will happen, and that's my theory, and I don't know how people have this on the radar, is what I'm really a fan of are the low-cost machines, for example. Because I lived through this FDM space. That was my life for many years. And what happened was, it's not that Stratasys doesn't sell high-end Fortus machines anymore that are really good quality and make amazing, like, aerospace-grade parts.
Mm-hmm.
It's just that there is a different category on the low-end space that is very distinct from it.
Mm-hmm. Mm-hmm.
And that has happened. And I think it will happen in any industry, in any technology that we see. So it happened in FDM, it happened in SLA. There are still big SLA machines, and there are small SLA machines. And it is happening in SLS. So there's the established player like EOS and the others, but they're all like the small machines from Format, for example, that cost like a unit factor, how do you say? Like one dimension less.
Yeah.
And have a different use case, but are much more affordable and so on. And it happens in the metal space too. It happens slowly, but it happens. So there are sub $100,000 machines. I'm a big fan of One Click Metal, for example, because we worked with them from the beginning, from a software side, from a toolpath side, but also they designed the machine in Fusion. So it's like my poster child example, but I'm a bit biased. But it's kind of, Björn and this team, they made from ground up, they were really experts in Trumpf, and they made this spin-off of Trumpf. That they really made the lowest cost metal AM machine possible, which has a small footprint, like 15 times 15. But if you are worried about cost, you won't print big parts.
Yeah.
So you need small machines somewhere, because the CapEx economics of the small machines are just a different league. Because at $100,000, everybody who can afford a milling machine can have an additive manufacturing machine for $100,000.
Yeah.
For $600,000, it's a very different game. You need to have an application that works. You need to have a runtime that works, that it makes it feasible. And the small machines, there's also for workforce developments to get into the technology, they are great. And if you look at it from a Western perspective, except One Click Metal and now a few others, I'm a bit worried that the Western machine vendors are a bit blind on that low-end side, to phrase it in that way.
But to your point earlier, right? There's always a space for both.
No, there's always a space for both. Don't get me wrong. I just think there will be the small end of the world, and there will be the high end. But the high end, and I mean EOS does it. I mean EOS has completely understand it. This is what AMCM is doing. Because if you spend $5 million on a machine that makes rocket ships, you want to have a custom spec, and that's happening. That is, if you ever went to a subtractive, and I had to learn so much about subtractives that I never wanted to know since being at Autodesk, but also like about CAD that I never wanted to know. And if you go to EMO, for example, which is the leading subtractive show every 2 years in Hanover, and there are like thousands of machine makers. Of course, there's like the leading companies like D&G Mori, for example. But there are like thousands of tail end manufactured and sell like 5 to 10 machines to special verticals that serve special needs in the making space. And my suspicion is that we will have the split of mass market, off the shelf machines, sub 100K, that are good enough for parts where the quality is not super critical.
Yeah.
And you can do a lot with software, with like overhang corrections, support structure optimization, with simulation-driven tool passing. You can do a lot of things in the mass market space that today are even not feasible. And so you will drive the quality up on the software side. But what we definitely will want to do is keep the quality we have and drive down the unit costs of the price.
I mean, and if you think about it, I mean, there are so many small mom and pop shops in the US, in Germany, all over the place, where the barrier of entry into large scale metal additive manufacturing is too big, right?
It's too big, yes. And I mean, a lot. If filling up the machine with powder costs you like your yearly
profit,
profit, then it's really complicated.
Yeah.
And both of these will coexist. But I think the real innovation, that's just me, my thing, the real innovations will come out of the low end, and the high end will have its existence and so on.
But and there's most likely also a step effect, right? I mean, I see companies that have 20 FDM printers or even 40 FDM printers as a print farm, then switching to more industrial equipment for certain applications, because now you get to a point where your overhead is super high because you need to flip a machine every 10 minutes now, right? It also, like, having a huge farm of these small systems at some point isn't scalable anymore, right? So I think it actually really helps also the established machine manufacturers to have smaller equipment competition that can open up the market, like you said, open up innovation. And then at some points, there is a scaling factor where large frame systems or highly productive systems that are a bit higher in CapEx then also make sense, right? So
no, don't get me wrong.
And vice versa.
This is a unit cost. So if you have a really large machine that prints parts as cheap as a small machine, and you have the unit count, that's very clearly the same. But my suspicion is also that will be a custom AMCM made machine. That's what I'm saying.
Yeah, for sure.
Because you want to tune the machine, the laser, the whatever, beam shaping to your application, and then make it affordable, I think. Yeah, these are the things. And then we haven't talked about AI yet. They will enable a lot of applications. Maybe that is something you wanted to talk to.
No, yeah, I do have AI on my agenda. I remember you and I talked at AM Strategies in New York about this a little bit, and I do think you have a very good viewpoint and grasp on AI. Same on what's overhyped and what's reality, right? It is also a tool that in other industries as well helps to lower the barrier of entry by simplifying certain tasks or making certain tasks more efficient, in my opinion. But yeah, what's your thought on AI? How is it in general impacting the additive manufacturing industry in the mid and long term? But also, what do you guys do at Autodesk to leverage that?
So before we go into it, I wanted to say with this split, we have a very good product strategy with split there, just to make a little bit of adjustment. So for the mass market, we have Fusion, which is really the solution for this. I think there is nothing comes close for this development of these mass market machines, because there you need affordability, ease of use, and all kind of things. And then with our backend technology, we are from Netfabb, and still our Netfabb product we also cater the high-end market. So for example, if you go to Formnext and see all these multi-material parts, every single one of them is a Netfabb part, for example. So we are in a very unique situation that we see both ends.
Yeah.
And it's a very exciting time to see this split happening, and also to see how the technologies drive it. I think that is something I am really about. And what one of the technologies that drives both is, this AI it really blew me away. Everything is AI these days, so they don't take it with a grain of salt. There's a lot of rebranding and hype and just putting your flag into the wind and all kinds of things.
Yeah.
What happened was, there is this LLM space that is like this assistance and so on. And I fear I can't pronounce products, but it's kind of, I was skeptical in the beginning, but seeing more and more applications from it, also from a workforce development side, it really helps you. And not only from getting into it, but also from like advising you and also explaining things. I've seen really interesting applications inside and outside of all of this, where people explain simulation results, for example. Where LLMs can explain to you their simulation results, because that is the problem always in FEA simulation. There's the one thing to have a simulation, the other thing is what you make out of it.
Yeah, okay, that's interesting.
And having somebody who just explains like a CSV Excel table in a human readable form that a standard engineer would understand, that's a big thing in many ways. So I think there is merit also in engineering. But what I think is, in the general sense, what really blew me away was when I got to know Omar and Katerina from Southern Kelvin. And I know a lot about, I got to know a lot about metal additive simulation because we own it and it's my team and we market it. And it's simulation. If you have process simulation itself, it's a game changer because you get the insights you never could have. And it's the only issue you have is it. And just to explain it, what works is you can do a very accurate, and we call it like, if you do a fine resolution simulation of the laser beam, how it moves with a simulation process. There are different solutions now, I think, but ours was the first in the market, and you can do like a mate pool level simulation of a layer, for example. That gives you super accurate making history, temperature history, and deformation history over the part. And that is awesome. And you can use it for material qualification. You can use it for looking into the process. But it's a hugely expensive simulation. So it costs for like a cube of like 5 millimeters cube. It costs like maybe 4 hours. For a centimeter cube, it costs already 24 hours to simulate the process.
Yeah. And
what happened is this simulation gives you really insights in everything that happens, like predictive. So you don't have fudge factors. You give it like the mechanic, like the physical properties, and you get like super lot of data of every point in space, how the temperature was at which time. And that is amazing. And of course, some people in the simulation community will say, yes, but microstructure and so on. That is what you derive from it. So there's a lot of things that real process simulation gives you. But the problem is the compute time. So what people did is they did what they call it a homogenization process. So we basically simulate the material behavior on a small scale and then map it. So either do that or do some experiments, but then map this on larger geometries. And that's called either inherent strain, or that's called, inherent strain is like the experimental thing. You also build some test parts and then map them. Or, what we do is we do some predictive process simulations on a small scale and then map the results on the big part process. And that means you can simulate the temperature, interlayer temperature history, and the distortion behavior of a big M400 build within like a few hours. That's possible. It's not so much depending on the real size of the machine. It's more depending on the on the small feature size, you want to have a resolution in your part.
And is that
lattice parts are much harder?
And are you now
than
talking about still like a more traditional simulation approach, or?
Well, no, this is simulation. So
Yeah.
they're talking the same.
Okay. Yeah.
And there is a lot of, so what you then can do is you can pre-distort your part and then get more accurate if you print the part that is pre-distorted, that distorts into shape. And that was the big change 10 years ago, that this was suddenly possible.
Yeah, and there were a few companies doing that. Also,
many companies. I mean, we have many customers from many simulation. They just do that on every part, and that's one workflow that you need to do if you want to. I mean, otherwise you run blind in a way. Well, you don't run blind because you have the process monitoring. That's another thing, and that's also where your Smart Fusion came out, because you can always use the simulation. So what you can also do with simulations is, for example, you can drive the energy that you put into a part. And we just released that in Fusion. So you can basically simulate your part, and then for each layer, you get the interlayer temperature, so you know when your part gets too hot.
Yeah.
You basically can then reduce the...
Sure.
And it's not only a layer basis, it's like a localized thing. You can locally
reduce power in a certain
power, for example, and then get like a better heat distribution in your part. And that is what Smart Fusion, for example, does on an experimental basis, but it has a much more accuracy, because
it's real time.
The homogenized simulation does not resolve the process good enough that you would capture all the features. For example, what you see in, how is it called? What drives Smart Fusion? Your process monitoring.
OT, optical tomography.
OT, yes. But there's others, and then basically see the turning points of, if you look at OT images, you see the turning points of the layers and things like that. And this interaction you see in simulation, but only in a fine grain simulation, and not in the homogenized simulation.
Okay.
And
which would take days.
It would take ages. We only see the
Yeah.
And that was always the blocker, while simulation was silently integrated into workflows on many places. But it wasn't some people will yell at me for this. It was not like the game changer that suddenly made every application possible. If you understand what I mean.
Yeah.
And then when I first met Omar and Katrina, I couldn't believe that they just surrogate modeled the fine grain simulation. And now the fine grain simulation doesn't take like 24 hours for small parts. So it doesn't only mean that you can only simulate a small part. It only means you can never simulate a full tray.
Yeah.
Because it would take like 50,000 years to simulate it, because it's not linear. So the more elements you have, the FEA is very complicated. Like how the runtimes work. And they found, this is like the genius, they found a surrogate model that works and seemed to match the process monitoring. And the simulation, of course. So the simulation this is purely simulation driven. So they simulate the process, and the process completely predicts on a super high accurate scale the
actual process.
The process.
Yeah.
So what means is basically this is what I call the next level after Smart Fusion, is basically you can do this all offline, and you predict the process and then can do all these adjustments that you do. You can do that already. Upfront. And that seems to work crazily well. And we see that also in other spaces. So Autodesk, I'm very happy that we finally that we did it in the end. But so Southern Cabin is from Berlin. I don't know why everything's in Berlin. There was another company in Berlin called Navasto. They did also surrogate modeling for generic FEA, and especially for automotive car design, like CFD simulations.
Okay.
And crash tests, for example. And it's really crazy. So you basically can, with a few examples, you can use Navasto to give it like 100 examples of your car, of different cars, and then do real CFD simulations on it. And that takes like 20 hours. And then you can use these 100 results and train a surrogate model. And from then on, for similar cars, you get the simulation result in like 50 milliseconds.
Wow.
It's like predictive mode of surrogate modeling is crazy and will change a lot of engineering workflows.
That is very interesting.
And I mean, they're an amazing startup. And by accident, we acquired them like, well, September or so. And now we put all these like CFD tools into our design tools. Like we start with Alias, which is car design, but of course we also will over time put it in Fusion. And that is really a game changer. Not only, I think what will hit engineering the first? Surrogate modeling, getting instant feedback on what you change. On the additive side, I mean, also with 1000 Kelvin, we did an integration. So we have an app store where there's a 1000 Kelvin app where people can, from Fusion, can optimize their parts and do the toolpath optimization. And I mean, the customers we have, we also recently launched a customer case story. It's really amazing. I mean, basically just make parts work that didn't work before.
Mm-hmm.
And of course, it's difficult because this is also, so when you speak of workforce development, because the question is also always how you market it. If you market it as like magic make button that just does everything for you, that's always a bit difficult. Because then, of course, everybody says, it feels challenged to like shut it down and all these things.
No, it's more like
if you see that like a progression of things that happen, and I really see it in that order. I really see process simulation, then things like, I talk about smart fusion because that's like the other thing, but like others are looking to do. So I think you go from simulation-driven optimization to process monitoring-driven optimization to like AI-driven optimization. And that's like a path that will just open metal additives for many applications. And this is really, I think this is really a path that is game-changing. And that is really something different that was just not possible 10 years ago.
Yeah. I mean, it has a few effects, right? One is, yes, there is a workforce aspect to it, or almost again, in additive historically, you needed highly experienced process engineers to develop application-specific parameters, right? Or even to build certain parts, because they looked at a part and they could tell you, no, it's going to build, or it's not going to build, right? Where maybe a junior engineer...
For 20 years, yes,
yeah.
exactly.
Yeah, or even 2 years ago still, right? Or a junior comes in and is going to try that build and it's going to crash. Whereas the guy with 10 years experience could have said, it's going to crash, don't even try it, right? And the simulation can take that part of that experienced person that can look over your shoulder and tell you it's going to build or not going to build. And then the next level is now you can optimize parameters for the specific application. So it can build, which also in the past would have required a very highly skilled, highly experienced engineer that can now be...
Yeah, or we just wouldn't have built. I mean, that's also what happens.
Correct. Or it wouldn't have built. Yeah.
But I think it is also something in the additive space that I learned from the subtractive space. We always think the subtractive space is the most professional space on the planet. And that's not true.
No. Yeah.
Because like breaking your end mill is a very common thing if your toolpath is not right. That's why there's toolpath simulation that simulates the toolpath. And also AI in the subtractive space.
Even that is complicated. I mean, I looked over the shoulder of somebody doing a toolpath simulation and building a toolpath. It's complicated. It requires expertise and experience. I agree. Yeah, it's not the
And this is in every manufacturing vertical. So I think it's okay for our industry to say that there are weaknesses in the technology, like in every technology.
Sure.
And we have these methods to mitigate them. And I think these surrogate model-driven AI tools will be will just play a very big role in making both things. When I talk to, there's a split in the market. They will make the high-end things work at all, and they will make the low-end things cheaper. I think both will happen.
Yeah,
because you can save material, you can save support structures, and if you do your post-processing better and your surface quality better on the small machines, then you will get better cost per part, or you might increase the quality to an acceptable level when costs don't matter. Yeah. So maybe, I don't know, maybe I said there is no solution. I've said before there is no solution if the part is too expensive and too crappy, but maybe there is, I don't know.
Yeah.
But that is, I think having a gradual down-to-earth thing that solves both of these problems, I think that is a great future for the additive in the industry. And we only talked about metal. I mean, there was a lot happening in plastic too.
Yeah. What's happening? What's the synonym on the polymer side when it comes to let's stick with the AI topic, right? I mean, there's also there's different challenges on the polymer side, but there's also
yeah, on the polymer side. What I'm a bit missing is the simulation piece on the polymer side. We have tried with our mold flow technology, and we didn't get very far.
Okay.
So polymer simulation is really complicated, and I bet people in your company have looked at it for a long time, and I have not seen a widespread adoption of simulation technology on the polymer side. And that is sad because it's a hot process, and distortion on the polymer side is a big issue. And I mean, I feel we don't have a great solution that nobody else has for it. So we do have Nastran and so on, but it's a complicated thing. You can heuristically attach it. So for example, we recently introduced a Nesta that does like equalization of layer times and things like that. That is great help. But where there is movements on the AI side, in the polymer side, and in the metal side. Of course, it's also primarily on the metal side because there's where the money is. But we also work with a company called Euler from Iceland.
Yeah.
I hope maybe they watch this at that point. They are great. Everybody should look at them. They made the best powder bed monitoring system that I have ever come across. So they use AI from standard cameras to see issues that you create in a powder bed.
Yeah.
And that gives you much more insight in the quality in the process. We haven't talked about this. So this is the third pillar. So the one pillar is LLM, which is more like an access, and it's more like an access to the technology thing. It's surrogate modeling, which will really drive change. And then the third one is like all the
monitoring,
all the visualization, all the feature recognition and optical.
Well, many about
the computer vision things of the element. And like I said, I'm a big fan of Euler because they really made it. Not only that they have an algorithm that does it, but they also integrate it in the right business model, which is like online monitoring, easy setup, 5 minutes, use standard hardware, all these kind of things, with some very clever ways of user interface ways of displaying the issues, filtering for the issues, monitoring the issues, predicting issues. So you will get like a notification if in 5 layers they think in 5 layers something will happen. You get like a text message or something.
Oh, okay.
And I want to advertise them, and they made an amazing Fusion integration that I can just encourage everybody to look at. So,
okay.
And that is also something that I think Autodesk can play a role on, because we have a lot of exciting AI developments coming that we usually release in September in our conferences. But Fusion, as in its affordability and breadth, is also a great mass market platform that if somebody solves one thing very good and very groundbreaking, it's always, and I work with a lot of startups in that space.
Yeah.
That if you have solved one piece of the puzzle, you still need 95% of the other things to implement the manufacturing workflow. And because we have a great developer platform and a great an app store and something, it is a really great. So I mean, I'm responsible for additive manufacturing, but my team does also, for example, manufacturing automation and also other things. And I work with a lot of startups that use Fusion as go-to-market, which means they have solved one specific problem, and then they suddenly, with a software that only $680, can extend their product to an end-to-end solution and then go to market with it.
Okay.
And that is something that I'm seeing that is really great. And for us, it's amazing because, I mean, we don't have endless resources on everything. So we partner with a lot of people that serve specific niches. And if somebody comes up with a toolpath algorithm that is just so much better, even if we have our own ones, we would also be very willing to I mean, we play more a platform play. We don't say this is our solution and it's a closed ecosystem. And that works very well for us. And so if any startup watches and you have a great technology, you need to go to market, then just call me and I will
reach
help
out to
you.
Alex. But that actually raises a question I have. So it dawns on me that you guys are playing a bigger role also in interchangeability. And what I mean by that is, if you now talk about startups, traditionally, for example, I talked to Arne Held regularly, or we had Danny Piper on the show, right? Who are both in the investment space, and typically, right, you investing in software, you expect a certain scale. Investing in hardware is way more difficult because the growth and the scalability are way more restricted and restrictive. And I think you mentioned that even earlier yourself, right? There's way more capital, equipment that needs to be acquired. So the journey is a bit slower and more difficult. But I could see a future where applications or products that are designed in Autodesk or with the Autodesk ecosystem, where maybe in the early stages, the whole product is printed because it's a prototype or a very low volume application. And as I scale, it seems to me that I potentially now have an easier way of switching manufacturing methods for one part in additive over to a machining operation, or from one polymer part over to an injection molding operation. And therefore, I can shorten my production ramp up by having all these tools available in Autodesk that work somewhat seamlessly.
Yeah, that's an integration story. So, like I said, I'm in the fortunate position that I have views on the specialist market and on the integrated market, I call it.
Yeah.
It is not, it's not that Autodesk is the only player who has like a CAD/CAM integration, but there are not so many players. And it's really the case that this integrated story is a compelling one to anybody.
Yeah.
Because just the change management, the tracking, the PLM system integration, all these kind of things that you get for free when you have a CAD integration is just trumping every specialist tool that you have from an organizational perspective, from anything. And I would a bit disagree what you said with the investment theory. And that is a little bit the problem that Arno has, I think, sometimes with the software, is the scaling of software is great if you make a photo sharing app. If you make manufacturing software for a manufacturing niche, your life is much harder in terms of scalability.
Sure, you have
because you're bound with the scaling of the market.
Yeah.
So you say the machines are limited, but the machines then limit the software market, if you understand what I mean. And that is a little bit the problem that I see also in the VC space, that if and that will happen in AI even more. But I think and that's just maybe because we come from Bavaria and we basically bootstrapped everything, but it's really difficult to justify a lot of outside investment.
Mm-hmm.
If you then make specialist software, if you understand what I mean.
Sure. Yeah.
Because if you get like $50 million from somewhere and then how much revenue will you need to make
within a very niche,
in order to
small target group? Yeah, I get it.
Yeah, because the addressable market is not so high. And I think, there is, manufacturing. Don't get me wrong, the manufacturing software market is exciting. There is a lot of very profitable players. But I think this VC model is very limited because you don't get the scale effects.
Mm-hmm. Mm-hmm.
And how did we go this route?
Well, I guess my question was more in general, not even looking at additive, but I don't know, let's say I'm a drone company or a robotics company, and I start to design my drone in Autodesk. Initially, I print everything, but now I realize I'm reaching volumes where in certain cases, maybe it makes sense to go to a more conventional manufacturing technology. That switch seems to be...
Yeah, and if you have an integrated solution that you have injection molding simulation at your fingertips, that is the story for Fusion.
And I can even
that
design
is how
my parts from the beginning, already anticipating that change. And then maybe in the long tail, where I have a new generation, but I need to service this application still with spare parts, I can go back to additive. So I'm opening up my tool belt from the beginning.
I see what it's saying.
A bit easier, huh? And that should also lower or increase the success rate and the scalability potential for these hardware startups that I think sometimes struggle with that transition.
Yes, but that is complicated because you need to that you can't print everything. That's one of. So my opinion is why the polymer market is not so. Well, there are two things to it. One thing is you really need to design for your process.
Sure.
So it's always a redesign. So just switching process, there is a lot of application development to it. And of course, you can replace an additive part when you get into higher number. That's what people actually do. I mean, I know a lot of small 3D printer, FDM, when they went into the thousands, they switched from laser cut parts to injection molded parts. I mean, that is natural. Mm-hmm. But that is more like an intergenerational thing. I think just switching technology without changing the design is not, if that is what you want to ask, that is not something that is very promising. I think that's also why, for example, all these scanning technologies that scan through your catalog and see what parts can be 3D printed. That is a very good pitch, but it always crashes with reality, in my opinion. Because you can't just take a casting part and then just 3D print it. I mean, you can.
Okay.
You can, but it's usually not the wisest business decision. And I mean, if you understand what I mean. So there must be other reasons. For example, there must be like you need to keep them on stock, and it's like you have like a supply chain issue. You can't get the part anymore, and all these kind of things. These are more the things that you need to account, and these are not. You wouldn't. If you really want to make your next generation product and switch technology, it will look different. That's what I wanted to say.
Yeah, I agree. But you could even already anticipate that you are going to injection mold it, but for the first 100,000 parts, you're going to print it, right? With the injection molded design. Yes, there's going to be maybe support structures if you're using FDM, or it's going to be a bit of an awkward orientation if it's metal, but you're going to print it to ramp up your production, to test out your market. And then you keep your design and switch it over to conventional.
Yeah, but I don't think. From my experience, that is prototyping, first of all. That's what we always do. Yeah. And what I see is also from my FIT days is you then would vacuum cast them, for example. The first 100 you vacuum cast, because then you have the same material as in the injection molding afterwards.
Okay.
If you understand what I mean. Because there are many manufacturing methods you have in terms of casting and so on. So it might change. I mean, there is a lot of Form Labs. This is really great in making these user stories where they say, okay, we print them because they are matching the injection molding. But the whole, since I know this, it was like, oh, we will go after injection molding from a polymer side. And the problem is, in my opinion, but some very smart people talking that. So casting is really shitty since 5,000 years. That's why it's easier in metal. Injection molding is a really good technology, which makes parts once you have written off your tool, you can make millions of parts really cheap at a really good quality with very little variance and all kind of things.
Yeah.
To compete with like SLS, for example, with that on like a head-to-head basis is just very difficult. And that's why we don't see it. So we don't see the shoes, the million shoes. We don't see we just don't see it in the market that there is so much application. And it always works where you have another reason. For example, in hearing aids, which is like the oldest thing ever, where they switched like a time out. And I think there needs to be another reason. And the design is only a vehicle, and the technology is only a vehicle to make a business impact. And it's always about I think it's always the two things. Can I make the part good enough? And no. Either I want to can I make the part at a certain quality and the cheapest price for the quality? And does this match my two barriers? I don't want to overpay the quality just because I can make it better, but I also need to match a certain quality and then have the lowest possible price. And is that price acceptable? That is how we always went into applications from a manufacturing perspective. And that makes it very complicated to hop manufacturing technologies.
Mm-hmm. That's a good.
But that's just my opinion.
No, it's a valid point. There's always multiple answers to a question, right? I do see your point. I do see other scenarios playing out as well, because there is nuances pretty much to every manufacturer out there. And I think there's, to your point, different reasons why additive makes sense. In certain cases, it's the design. In other cases, it is the supply chain, or it is the volumes. It's hard to.
Yeah, the only thing we can contribute is we can really make a really good mass market tool that allows you to design anything in any technology. That's what we do.
Yeah, and that's
and it's affordable too. So
yeah, and that
if you use any metal additive machine, I think we really have the most competitive solution in the market. Almost. I mean, plastics anyhow. For $700, you get a 3D nester. Where do you get that?
Yeah. Well, Alex, this has been a really awesome conversation. I learned a lot about the history of additive. Even I've only been in the industry for 10 years. You've been in the industry since 1998, I think you said. So
yeah, it's too long. I think it's too long. I should. But no. So this is our job. People think that engineers will be replaced by AI and all these kind of things. And my theory is it's a little bit like self-driving. So it works awesome until it kills you. And I think also in coding, for example, is it so we will have tools that help us a lot in the future.
Mm-hmm.
And once the day comes that it's like an AI completeness thing. So once the day comes that you don't need engineers anymore, then you don't need humans anymore. That's my theory. And when you don't need humans anymore, then you need to find something else, maybe gardening or something.
Yeah, maybe we go back to the good old days and we all have a farm. Yeah. Who knows?
Yeah.
Who knows?
That's what I wanted to say. So I'm too long. Maybe I should go to the farm. That was why I came to this. Anyhow.
Yeah, but
thank you for the invitation. It was a great discussion.
No, Alex, it was really awesome to have you on the show. I hope you'll come back. I think you're one of those individuals in the industry that have a very realistic view on additive. You've seen the manufacturing space. You've of course continues to see the software space, which is ever evolving. So I'm sure if we invite you back on the show in half a year, we can have a completely different discussion, because there's 5 new tools out there, and you guys have launched new tools as well. So
yeah, and I think it's changing a lot. I think also. So let's see what the future brings. I think the more normal the technology becomes, the better it's for everybody.
Yeah,
and I really hope that EOS is continue pushing this normalization process. And thank you for inviting me.
It was a pleasure. And to our listeners, it was a pleasure having you join us for this recording. If you like this episode, share it with a friend, colleague, or whoever you think might enjoy Alex's and my conversation. This was the Additive Snack Podcast, and I will see you next time.
Thank you. Bye-bye.